Welcome to SS2 Further Mathematics, Term 3, Week 11. Game theory is the mathematical study of strategic decision-making, situations where the outcome for one decision-maker depends on the decisions of others. Developed by John von Neumann and Oscar Morgenstern, 1944, and extended by John Nash, Nobel Prize 1994, game theory has applications in economics, politics, evolutionary biology, and military strategy. By the end of this lesson, you will define basic game theory concepts, analyze two-player zero-sum games, find saddle points, solve mixed strategy games, and answer WAEC further mathematics questions. Let us begin. Basic terminology: a game involves two or more players, decision makers. Each player has a set of strategies, available choices. The payoff is the gain, or loss, to a player for each combination of strategies chosen. A two-player zero-sum game is one where the gain of one player equals the loss of the other, their payoff sum to zero. This is the simplest and most studied type of game. Payoff matrix: a table showing the payoffs to the row player, player A, for each combination of strategies. Rows represent player A's strategies, columns represent player B's strategies. If player A's payoff is shown, player B's payoff for the same cell is the negative of that value, zero-sum. Example payoff matrix: player A's gains from player B's strategies B1 and B2 for player B, strategies A1 and A2 for player A, B1, B2, A1, A2. If A plays A1 and B plays B1, A gains 4, B loses 4. If A plays A1 and B plays B2, A gains 2, B loses 2. If A plays A2 and B plays B1, A gains -1, B gains 1, A loses. If A plays A2 and B plays B2, A gains 3, B loses 3. Player A wants to maximize their payoff, player B wants to minimize A's payoff, equivalent to maximizing B's own payoff. Minimax and maximum strategies: player A's maximum strategy: for each of A's strategies, rows, find the minimum payoff, worst case, choose the strategy with the maximum of these minimums. Player B's minimax strategy: for each of B's strategies, columns, find the maximum payoff to A, worst case for B, choose the strategy that minimizes this maximum. If the maximum of A equals the minimax of B, a saddle point exists. Saddle point: an entry in the payoff matrix that is simultaneously the minimum in its row and the maximum in its column. Example: payoff matrix, A's gains. Row minima: min, 4, 2, equals 2, min, -1, 3, equals -1. Maximum equals max, 2, -1, equals 2, A plays strategy A1. Column maxima: max, of 4, -1, equals 4, max, 2, 3, equals 3. Minimax equals min, 4, 3, equals 3, B plays strategy B2. Maximum, 2, is not equal to minimax, 3, no saddle point in this example. Let us try another matrix. Row minima: 3, 2, maximum equals 3, row 1. Column maxima: 5, 4, minimax equals 4, call 2. Maximum, 3, is not equal to minimax, 4, no saddle point. Another try. Row minima: 3, 4, maximum equals 4, row 2, strategy A2. Column maxima: 6, 4, minimax equals 4, call 2, strategy B2. Maximum equals minimax equals 4 saddle points at entry E2, 2. Value of the game equals 4. A plays A2, B plays B2, pure strategy equilibrium, Nash equilibrium. When no saddle point exists, both players should use mixed strategies, randomizing between their pure strategies according to optimal probabilities. For a 2x2 zero-sum game with no saddle point, payoff matrix. Player A plays strategy A1 with probability P and A2 with probability 1P. Player B plays strategy B1 with probability Q and B2 with probability 1Q. Optimal P for player A: the expected payoff to A should be the same whether B plays B1 or B2, making B indifferent, so B cannot exploit A's randomization. Expected payoff if B plays B1 E1 equals P plus 1P, C. Expected payoff if B plays B2, E2 equals PB plus 1P, D. Set E1 equals E2, P plus 1P, C equals PB plus 1P, D. P, A, B plus C, PC, D, PD equals 0. P, A, B, C plus D equals D, C, P equals D, C / A, B, C plus D. Value of game to A, V equals rad BC / A, B, C plus D. Optimal Q for player B, similarly, V equals D, B / A, B, C plus D times A plus, simplifying, Q equals D, B / A plus D, B, C. Worked example, matrix. A equals 4, B equals 2, C equals -1, D equals 3. P equals D, C / A, B, C plus D equals 3, -1, / 4 to 2, -1, plus 3 equals 4 / 4 to 2 plus 1 plus 3 equals 4 6 equals 2/3. Q equals D, B / A plus D, B, C equals open parenthesis 3 minus 2 close parenthesis divided by open parenthesis 4 plus 3 minus 2 minus open parenthesis minus 1 close parenthesis equals 1/6. Value V equals I add BC / A plus D, B, C equals 4 by 3, 2 times, -1, / 4 plus 3 - 2 plus 1 equals 12 plus 2 / 6 equals 14 6 equals 7/3 is almost equal to 2.33. Interpretation: A plays A1 with probe 2/3, A2 with probe 1/3, B plays B1 with probe 1/6, B2 with probe 5/6. Expected payoff to A equals 7/3. Nash equilibrium. John Nash, 1950. A set of strategies, one for each player, such that no player can benefit by unilaterally changing their strategy. In zero-sum two-player games, the saddle point, pure strategy, or mixed strategy solution is always a Nash equilibrium. The prisoner's dilemma, a famous non-zero-sum game. Two suspects are arrested and held separately. Each can cooperate, stay silent, or defect, betray the other. Payoff matrix: if both cooperate, both get 1 year. If A defects and B cooperates, A goes free, 0 years, B gets 5 years. If A cooperates and B defects, A gets 5 years, B goes free. If both defect, both get 3 years. Nash equilibrium: both defect, mutual defection, even though both cooperating would be better for both. This illustrates why collective action problems arise. Individual rationality can lead to collectively worse outcomes. Real-world applications of game theory: oligopoly pricing, Cournot, Bertrand models, arms races between nations, auctions, bidding strategies, evolutionary biology, evolutionarily stable strategies, ESS, traffic routing, negotiation and bargaining. Nigerian context: game theory models pricing decisions between market rivals, e.g. two competing petrol stations setting prices, negotiation strategies in business, and international trade policy. Key points: game theory studies strategic decision-making where outcomes depend on all players' choices. Zero-sum game: one player's gain equals other player's loss. Payoff matrix: rows equals A strategies, columns equals B strategies, entries equals A's payoff. Pure strategy saddle point: entry that is minimum in its row and maximum in its column. Exists when maximin equals minimax, value of game. No saddle point mixed strategies. Optimal mixed strategy: choose probabilities P and Q so opponent is indifferent. For 2x2 game, P equals DC / ABC plus D, Q equals DB / A plus DBC, V equals at BC / A plus DBC. Nash equilibrium: no player can improve by changing strategy alone. Prisoner's dilemma: both defect even though mutual cooperation is better, illustrates tension between individual and collective rationality. WAEC test: identify saddle points, find maximin and minimax, solve 2x2 mixed strategy games, state optimal probabilities and game value.